this leap or a jump in trying to do galaxy formation in a more realistic fashion. And these are just some examples. There's an Eagle project, the Horizon AGN project, Magneticum project, obviously Illustris that you all know about, and Illustris TNG, and also Massive Black 2, and there are several others as well. So what was really the key behind the success of these models and why this resonated in the scientific community? That was for the first time, essentially, these simulations could reproduce morphological diversity of galaxies for representative samples of galaxies. The way how this morphological diversity came about, there are subtleties about this, so there is not a single kind of ingredient or a single part, but all these different simulations now started to reproduce something that looks like elliptical galaxies, something that looks like disk galaxies, and something that looks like irregular galaxies. And one of the key ingredients, which I will question to some extent later on, of these simulations has been the supermassive black holes. So in all these different models, done independently by different people, if you wouldn't put the feedback processes from supermassive black holes, you wouldn't get this result, which is in a way kind of encouraging, telling us maybe there is something deeper about this and we have to think harder. One specific example is here from Horizon AGN. If you just repeat the whole expensive simulation once more, but switch off AGN feedback from something that looks at the massive and elliptical galaxies, you go to something that looks over massive star-forming disks in the low redshift universe, and this is nothing like we observe. And this is like a simple numerical test that you can do to convince yourself that there is something in the feedback from supermassive black holes. We can look at that a little bit more deeply and find a correlation between the black hole properties and the ones of galaxies. This is from my paper from 2015. And essentially, if you plot the black hole mass versus the stellar mass of the galaxy within the half-mass radius, you find this interesting correlation. The more massive the black hole is, more feedback becomes important, more galaxy color becomes redder, more morphology of the galaxy transforms from a disk-like dominated structure to spheroidal dominated structure. So I want to tell you now, skip a couple of years and tell you about more recent developments in this area and where we are at. So first of all, I would like to talk a little bit about the Fable project. This is led by my PhD student, Nick Hendon, back in Cambridge. And what we have done here, we have done 27 high-resolution simulations of galaxy clusters, where we expect some of the most massive supermassive black holes to be. And we have tried to adopt the following approach. Given these limitations of the subgrid physics, which I mentioned, we have to calibrate some of our free parameters against some observables. And what we have done here, we have calibrated them to reproduce the stellar mass function to a reasonable accuracy against the observational data. So our colors are these bluish ones, and the data is the gray symbols. But also with respect to Illustris, we have changed some of parameterizations of the models, such as to get the gas mass fractions in galaxy clusters roughly in agreement with the X-ray observations. And that allowed us then to, so these are not the predictions of the models, let me put this clearly, this is just our calibration, right? So this shouldn't be seen as a success. Let me tell you a little bit what can we learn then from this type of simulations. And we can learn usually something where something doesn't work. That tells us about important bits of physics that perhaps is missing, or about some systematics that is important. So I want to highlight two systematics here. One is that we can now compare our simulated sample of clusters against the observations. So here I'm showing you M500, the mass within the R500 versus T500, that's the temperature in kiloelectronvolts, against two types of data. So these are the data from X-rays, and these are the data taken from the weak lensing. And you can see in one case we agree with the data, in the other case we don't agree. And obviously the simulation is always the same, and this is hinting toward this problem that has been actually known in the community for a number of years now, but it's still a pressing and unsolved problem, that there is a large hydrostatic mass bias when trying to estimate the cluster masses from the X-ray observations, and this is to the level from our simulations if we try to calibrate this out at a 20 to 30%. And so this has really important implications for cosmology. So what is this telling us? That we even have to do better simulations in order to be able to better calibrate this mass bias and account for it when we try to do cosmology from, let's say, the X-ray measurements. Another interesting thing, it comes from Nick's papers in PrEP that will come out soon, and this is if we want to look at the SZ properties of galaxy clusters. So what we have done here, we can compare, first of all, the dependence on the Y500, so this is the Sinaev-Zeldovich signal from the cluster against the cluster mass. We have compared our results, which is in blue, against a bunch of other simulations as well as observational data. So you would say from this plot, even though it spans many orders of magnitude in the log scale, so it's a bit deceiving, that this looks actually quite a good agreement with the data. So we are getting roughly the SZ signal in the simulations right against the observations. However, if you look a bit more carefully, you can see that there are some discrepancies both in the simulations and observation, especially at the low mass end, and this is the end where AGN feedback is thought to play even a bigger role because in galaxy groups the potential welds are shallower. So if we translate now this uncertainty in this scaling relation between Y500 and M500 into the predicted cluster count for the next generation of SZ service, we find a really interesting result. So we can do some limiting cut in Y500 for a survey like SPT3G, so what should they be able to detect in future, and then we count the number of objects per redshift bin as a function of redshift, and we get all these different curves. So some is our own stuff, which is the blue lines, some is from other theoretical predictions, some is from expectations based on current observations that obviously don't probe the low mass end of clusters that the future service will do. And here what you can see that there is actually considerable uncertainty in predicting this number. So anything ranges, let's say a redshift of 1, from 4,000 to 6,000 predicted counts in the future SZ service. And this is again a big uncertainty for cosmology if we want to calibrate the masses of these systems, because we don't know from observations yet what is happening at the low mass end, and we have a theoretical uncertainties in the modeling of the low mass end. Okay, so let me now take a step even further back and take a little bit more a critical view of the whole field. So I want to go back to this plot to highlight a really important result. So if you look at the stellar mass function, which is really one of the fundamental ingredients that we want to get right in galaxy formation simulations, and you look at all these different simulations like ours or Illustris or Eagle, or there are many others, what you can see to a certain extent, they all agree quite well with the data, which is encouraging, no? But at the same time, you can flip the coin around and you can say, what is actually the predictive power of these simulations if we use a different subgrid models or different physics and we achieve similar level of successes or similar level of results? What is the level of fine-tuning that we are actually doing in this type of simulations in the subgrid models to achieve this type of results? What is ultimately the purpose of these simulations, whether they should be a simple fitting exercise, and how can we actually go away from this and learn about the fundamental underlying physics? And this is what I would like to focus on to the rest of the talk. So I want to tell you a little bit about the numerical technique that we have developed together with my student, Mike Curtis, a couple of years ago back in Cambridge, where we have tried to address one of the most obvious shortcomings of this type of simulation, and this is the limited dynamical range. So we have developed a technique where we can resolve targeted spatial regions around supermassive black holes with much higher mass and spatial resolution, and this is shown here. So this is, for example, a simulated image of a galaxy. This is just a density map, and we can zoom in a little bit inside and show how the underlying computational domain looks like. In this particular case, is this Voronoi mesh from the moving mesh code Arepo, and we can then zoom in further to show how much we can gain in resolution if we adopt the algorithm that we have developed here. So let me show you a little movie to illustrate this more clearly. So this is a galaxy, it's evolving as a function of time. We are showing how the mesh is refining in the central region. You can see the X and Y scales are scaling in. So we can actually go by 8 orders of magnitude in resolution in the mass resolution to improve essentially our understanding what is happening in the vicinity of supermassive black holes. So the first striking result that came from this exercise was that the feedback effects are different if you have significantly different resolution. This is shown here. So this is showing temperature maps in the central region of a galaxy. In one case, we just do the standard thing that everybody does, so we don't change the resolution as we approach a supermassive black hole that is just sitting here in the center, and we are just spherically dumping some thermal energy around supermassive black hole in the host galaxy. In the other case, we are using this, what we call the super Lagrangian refinement, to really increase the resolution in the central region. And we dump exactly the same amount of energy there, but we see a very different picture. In one case, we have like the Z-Taylor spherical blast that comes from the center of the galaxy, essentially pushes all gas out and makes the galaxy void of gas. In the other case, we have a collimation due to just the pressure forces of the cold gas that is rotationally supported in the disk, I'll come to in a second, that actually makes this outflow initially, which is injected spherically, to become